The vibration properties of the system is described by the frequency response functions. There are two more frequently chosen alternatives to the frequency response function. One is the impulse response function, demonstrated with this system. If I hit this, then it performs a response, a vibration response to this impact. And if I can measure this properly, then I can process the measured data in order to achieve or estimate the vibration properties of this system. A third alternative is the system transfer function. In this presentation we will introduce the system transfer function and a specific representation, a specific form of the system transfer function, which I denote the system pole residue representation. And that representation will show to be extremely useful for interpreting the vibration properties of the system. We have three frequently used system characteristic functions. First of all, we have the system impulse response function, which is basically the response of the system when it's impacted with a short pulse. Mathematically speaking, a Dirac delta function. Then we have the system frequency response function, h of omega, where omega is the angular frequency, and that is defined as the Fourier transform of the impulse response function. And then finally we have the system transfer function, which is the Laplace domain correspondence of the frequency response function. So it's defined as the Laplace transform of the impulse response function. And the standard choice when you want to describe the characteristics of a system, dynamic system, is the system transfer function. So, for example, if we consider a multiple degree of freedom system like this, we have a number of masses, and and they are connected with a number of springs and dashpots, and we also have a number of forces, external forces, exciting this system. Now, as you know, the equations of motion for this system can be written in matrix vector form, where the M, D, and K matrices is the mass, damping, and stiffness matrices. And the X here is the displacement vector, and F here is the exciting force vector. And in the Laplace domain, if we perform the Laplace transformation, we replace the time derivatives with S, the Laplace variable S. So this means that the system transfer function H between the excitation force Fn in degree of freedom n and the response in degree of freedom m can be defined, as you know, as the ratio of x over f in the Laplace domain. So from the solution of this linear system of equations, you can, after some algebra, find this expression, and if you perform some more algebra, you can find that the system transfer function we had before can be expressed in this case as a ratio of two polynomials, one numerator polynomial and one denominator polynomial. And the variable here is, of course, the Laplace variable s. And one can show now that in this case, well, in all cases here, the numerator polynomial is of lower order than the denominator polynomial. And one can also show that p here, the order of the denominator polynomial, must be 2 times the degrees of freedom of the system. And those are two valuable properties that we can make use of later on. So one useful reformulation now is to use a Laurent series expansion. And because, well, since the numerator polynomial is of lower order than the denominator polynomial, we can actually write this polynomial expression as this type of Laurent series expansion. The numerator coefficients here are denoted residues, and the S1 and SP's here in the denominators are called system poles. That is the poles, the singular points of the denominator are defined as the system poles. So this means then that we can write the system transfer function as a sum of residues over S minus the poles, like this. And this I will denote as the pole residue form of the system transfer function. And we will continue working with this, and because it's valuable to see some physical interpretation of what this really is. And it will also later on in the course form useful formulation for identification of the model parameters from measurements, actually. So one useful property now is that both the numerator and denominator polynomials have real valued coefficients. Because of this, the complex conjugates roots theorem from linear algebra tells us that both the numerator and denominator roots are either real valued or appear in complex conjugate pairs. So that means that the system poles, which are so important for us, are real valued and or complex conjugate pairs. And also, this also goes, of course, for the residues. So, considering this, we can write system transfer function like this as pairwise, as pairs of terms with residues and poles complex conjugates. For example, let's look at a car, and let us describe the car with a bicycle model that is a 2-degree of freedom system. And one of the degrees of freedom is the vertical translation of the center of mass, and the other one is the rotation around the center of gravitation. So the governing system of equations now is a 2-degree of freedom. It's a coupled system of 2 differential equations. And with the motion degrees of freedom equal to the translation and the rotation. And then we have a force and a rotational moment then as external forces. So a numerical example like this gives us, after converting to Laplace domain and a Laurent series expansion, the following pole pairs. So we have a set of, one complex conjugate pole pair equal to this. We have small real part, negative, and a pair of imaginary parts, like this. And it gives us a second pair, like this. And to the first pole pair, S1, corresponds a residue pair, R1, like this. And to the second pole pair, we have a second residue pair, like this. So, how do we now interpret this? Well, if we plot the absolute value, that is the magnitude of the system transfer function, versus the Laplace variable, we get this nice looking graph. So here we have the imaginary part of the Laplace variable, and here is the real part of the Laplace variable. And this, on the vertical axis here, we actually have the base 10 logarithm of the absolute value of the system transfer function. As you can see here, we have 4 distinct peaks, and those correspond then to the poles. And since the poles, you know, are the roots of the denominator polynomial, it's clear that these are singular points of the system transfer function. So at these poles, actually these peaks tends to infinity. So we have 4 singular points, 4 poles corresponding to the 4 roots of the denominator polynomial. So let's now zoom in on this part of the function. So here you can see that the S1 and S2 poles actually are displaced from the imaginary axis with a small real part, as we saw from the numerical example. So what does these correspond to, and how do you interpret these things? Well, let's start with the frequency response function. The frequency response function is actually equal to, well, a special case, you can say, of the transfer function, because it's actually equal to the transfer function evaluated on the positive imaginary positive imaginary s-axis. So that means then that you can find the frequency response function as the red curve in this graph. So it's actually along the positive imaginary Laplace axis. So this is the frequency response function. So it's a small set of the system transfer function. So what happens now if we increase damping? If we increase damping, then we see that the poles are actually displaced even more from the imaginary axis. So the real parts will increase. Well, they will decrease to larger negative values. And that means then that the peaks, the infinity peaks, the singular points will be displaced from the imaginary axis. And that means, of course, that the peaks of the frequency response function will be smaller in magnitude, since the peaks are, well, the imaginary axis are further away from the infinity points of the transfer function.